Hi, Assalamualaikum warahmatullahi wabarakatuh. This section is to understand what happened in finite element approximation of PDE when H goes to 0. To answer this question, we need to understand Sobolev spaces, which are spaces which have weak derivative, and we've got Sobolev inequality. We also learned that the spaces are complete, and that means that they are subject to Lex-Milgram theorem. What can we do? We take a linear variational problem. So here in topic 3, variational formulations of PDEs, we consider linear variational problems defined on HK spaces by taking a bilinear form BUV and linear form FV. We seek a solution U in HK, Sobolev space, such that BUV equal to FV for every V test function in HK. Since HK is a Hilbert space, the Lex-Milgram theorem can be used to analyze the existence of a unique solution to an HK linear variational problem. For example, Helmholtz problem. Okay, this is the equation of Helmholtz equations. The Helmholtz problem solvability is immediate. In Theorem 13, while Posner's for modified Helmholtz, the Helmholtz variational problem on H1 satisfies the conditions of the Lex-Milgram theorem. Next, we develop the relationship between solution of the Helmholtz variational problem and the strong form Helmholtz equation. The Helmholtz equation is given by U minus gradient square U equal to F, and del U del N equal to 0. This is the condition on the boundary. The nice thing is that all technique we just used to show this solvability and stability for finite element discretization can be applied to the variational for the PDE itself. The basic idea is to check that when you take a solution of the Helmholtz variational problem and integrate by parts, then you reveal that the solution solved the strong form equation. Okay. Functions in HK makes boundary values hard to interpret since they are not guaranteed to have defined values on the boundary. So we make the following definition about a trace of H1 functions. In this definition, let U in H1 omega and choose UI a sequence such that UI is converged to U and U is in C infinity space. We define the trace U on the boundary as the limit of the restriction of UI to the boundary value. This definition is unique from the uniqueness of limits. Then we can extend our trace inequality for finite element functions directly to H1 functions. Lemma 15, this is a trace theorem for H1 function. Let U in H1 for a polygonal domain omega, then the trace U on the boundary satisfy the U norm, L2 norm is a finite. It is less than a constant times the H1 norm of U. The interpretation of this result is that if U in H1 omega, then U at the boundary is in the L2 on the boundary. This tells us when the integration by parts formula makes sense. Okay, in lemma 16, this is the formula of integration by parts. Okay, so when you have this integration, you can decompose into these two terms based on the formula of integration by parts. Now we have everything we need to show that solutions of the strong form also solve the variational problem. It is just a matter of substituting into the formula and applying integration by parts. Lemma 17, for f in L2 and let u in H2, we solve the Helmholtz equations with the boundary conditions in the L2 sense, which is the subtraction on the left hand side to the right hand side, L2 norm equal to 0. Then U solves the variational form of the Helmholtz equation. Now we go to other way, showing that solutions of the variational problem also solve the strong form equation. To do this, we need to assume a bit more smoothness of the solution, that it is in H2 instead of just H1. Theorem 18, let f in L2 omega and suppose that u in H2. Solve the variational Helmholtz equation on a polygonal domain omega. Then you solve the strong form Helmholtz equation with a 0 Newman boundary condition. So that is the theorem. Next, we will learn about the Galerkin approximation of linear variational problems in the next video.